Somos 11. Muy bien. Good morning. Buenos días a todos. Good morning, everyone. So welcome to the second day of the workshop on fatigue of plain and fiber concrete, plain and fiber reinforced concrete. So today our first speaker is Professor Alfonso Fernandez Cantelli. He's an emeritus professor from University of Oviedo. He got his, he's a mechanical engineer, got his PhD from the Polytechnic University of Madrid. His research interest is focused on the probabilistic modeling in fracture and fatigue of metals, polymers, and quasi-brittle materials. His work has been awarded by the Medal of Spanish Group of Fracture in 2016. He was recognized as the Distinguished Engineer or Ingeniero Laureado by the Spanish Royal Academy of Engineers 2019. Also, he won the Robert Moscovic Award of Merit of Essays in 2019. Go ahead, Alfonso.
Thank you, Rina, for the introduction. In this case, we are presenting the fatigue regression models in concrete, which are based on compatibility and sample functions based on the damage evolution. And this is a cooperation with my colleagues from the Royal Academy, Enrique Castillo, and Royal Academy of Science in Madrid, in Spain, and Sergio Blason from the BAM in Berlin. As an index, I will introduce the problematic and then to present the phenomenological model of independent random results, which are based on regression and compatibility, and particularly the basic SN model. Then, as a counterpart, the phenomenological stochastic models of cumulative damage evolution, followed by some examples of application for both fatigue and fracture phenomena, and finally, so very short concluding remarks. The problem of the fracture mechanics characterization of plain and fiber concrete is difficult because this material is quasi-brittle, and then the weakest link principle is not valid to be applied in general. And then the fracture process zone plays an important role in the establishment of the size effect, for instance, which interpreted by Bazant as intricate size-dependent problematic definition of the concrete strength. So there are different arguments to justify the use of the fracture mechanics in the case of the concrete and plain and fiber concrete as the energy criteria, crack propagation, the necessity of ambiguity in the results interpretation, size effect, and so on. And all these point out the necessity of resorting to fracture mechanics criteria to ensure a reliable design and safe of plain and fiber reinforced concrete structures. For instance, in the case of the conventional design using the strut and tie models, which is also called the stress fields, we need to know the effective strength. It means the characteristic values of the failure stress to be applied to the compression struts. And for this, we need to know which is the influence of the cracks, the duration of the cracks in the orientation of the strut or transversal to this. So only as an example. For us, the important question is that the characterization of materials in fracture and fatigue are two possibilities of to assess the experimental data corresponding to two different phenomena. The first one are tests which imply random experimental results, it means one test for one data point, which are statistically independent and are referred to the terminal state, which is not necessarily failure. It could be, for instance, a certain level of damage. In the second case, we are concerned with the stochastic process realization of damage accumulation phenomena, in which we get many data points only in one test. And this is from the record of the experimental evolution of a certain physical variable, which could be acoustic emission, deformation, etc. And in this case, we are, for instance, handling the epsilon and fatigue curves, or the P delta curve, or PCM, or the delta curve for this. So in the first case, we consider that this is necessary, the application of regression models, which are based on the compatibility between the distribution for the number of cycles given delta sigma, or for the distribution of delta sigma given the number of cycles for this. In the second case, we can apply this with using phenomenological model to define sample functions which normalized can be identified as cumulative distribution functions. Note that the SN field is a particular case of the second, because in the second, the use of the monitoring could be ignored and only concentrated to the terminal results of the test. So according to this, we propose the use of phenomenological models as justified by Freud and Tal, which consider that by applying the fundamental rules of the theory of probability, many of the experimentally established relations between the principal variables can be theoretically deduced from the purely formal assumption of the existence of a statistical distribution function, in this case, applied to cohesive bonds. It is to note that Freudenthal is widely regarded as the founder of the field of the structural safety and reliability, encompassing both the theories of probability and the statistic and the theories of mechanics. According with this, we propose to handle three cases. First, the assessment of the SN field. Second, of fatigue compressive test. And finally, the P delta or PCM test. These evaluations are important because they provide information which can be used or must be used in the practical fracture and fatigue design analysis of fracture energy, scale effect, and also in the application to cumulative damage calculation. We pass to the second point with the phenomenological models of independent random variables. In the case of the SN model, the evaluation, we consider that a virtual sample function, which can be imagined as resulting from testing only one specimen, but at different driving forces, sigma. In this case, we take the maximum, but could be also considered delta sigma. So for each specimen, we get a deterministic virtual SN curve. And then from this set of curves for the sample, then we can determine the percentile curves for the whole SN field of this. This is what Xi et al. Calls the principle of fatigue life probability percentile consistency, although we have already formulated this in 2005. So for the derivation of the model, we have to consider the following condition: physical conditions, which imply a limited tension range, delta sigma, and normalization to be applied for the different delta sigma levels in the principle of the weakest link. But at the same time, we need also to fulfill statistical conditions which imply dimensional consistency in the normalization in order to accomplish the reciprocity principle implied in the accelerated test. Then we need also to fulfill a stability condition in order to satisfy the location in the scale transformation. The limit behavior implies that we have to use an extreme value family, and we don't need to discuss which is the real distribution for the particular material tested, because we are only interested in low probabilities of failure. And then asymptotically, any distribution, statistical distribution, must be represented by one of the three extreme value distribution. It means Frechet, Gumbel, and Weibull. So finally, for us, we consider that the compatibility conditions, as mentioned before, between the two distributions in the horizontal and vertical sense is very important. So according to all these conditions to be fulfilled, the condition of minima, because we are concerned with the principle of weakest link, and the bounding of the lower tail, because we must apply a positive delta sigma and consider as compression, and a positive number of cycles indicate that the problem is bounded on the lower tail, and then accordingly the essence field must be represented in the lower probabilities of failure by a Weibull distribution for minima. Only two examples of the consideration of the compatibility as presented by Freudenthal and Gumbel. This is exactly the publication of these authors, and the same of Bolotin, considering the compatibility in this, which is the necessary condition that the essence field must accomplish. So the question is that if we have a Weibull distribution as represented here, we can consider that the lambda is only a function of the number of cycles in the case of the representation of the vertical distribution. In the case of the horizontal distribution, the lambda and delta, so the location in the scale parameter and the same as the shape parameter, must be only a function of the driving force delta sigma. So by applying the compatibility, a functional equation is resulting as represented here. And the only assumption we have made is that the shape parameter must be the same in both cases. Then the solution of this functional equation, which is a part of the mathematics that could be considered in parallel to the differential equation, provide only two possible Weibull models for minima. And these are the model 1 and model 2. But the model 2 is degenerated because the 0 percentile curve is evolving to be the asymptotes of this. The interesting question is that one of the model parameters, the C, represents the endurance limit, and B is the threshold of the number of cycles which must be conducted before a possible failure can be arise. And lambda, delta, and beta are the location, scale, and Weibull shape parameter. And in the second case is another scale normalization parameter, but we will only consider the model 1 as a possible for this. So the model parameters are estimated in two steps. The first are the asymptotes estimated, and then according to this, we can normalize all the results in this way using the view normalized variables, which is interesting because it's summarizing all the information represented in the SN field as a single variable distribution, so that it is irrespective of the driving force. We can assess all the results together, and then this is represented by a single variable distribution. This implies a reduction of the required number of tests, higher reliability, and an optimal, the possibility of an optimal test planning strategy, as Sergio Blasón will present in the following presentation. So we can relax the condition of the variable distribution, assuming the Gumbel, which is in transition between the variable and the threshold, when the shape parameter is higher than 6. And then in this case, we have a reduction of one parameter in the model. The size effect can be considered included in the model, so in a very easy manner, although in the case of non-uniform distribution in the specimen, we have to resort to another models. The runouts are included in the parameter evaluation using the expectation and maximization algorithm, and then the confidence interval of the percentile curves in the SN field may be estimated by applying the bootstrap method or using the Bayesian techniques. According to this, we prepare the ProFatigue software, which allows the model parameter to be determined. And this will be discussed in detail by Sergio Blasón. And then this is only to mention that this model, called the basic model, has some weaknesses, as for instance, due to the absence of the upper limit of delta sigma contradicting the existence of an ultimate stress sigma u, and the interpretation of the B parameter is not easy or fully understood, although Bolotin's model presents a similar parameter derived from micromechanical consideration. And then this model is derived for constant stress level condition, for instance, for R constant. And when the life prediction is intended for different stress level, we have to extend the model. And the same when the non-uniform stress distribution, for instance, in the specimen, requires to be complemented with a generalized local model. All these problems have been enhanced now using what we say a general model, which overcome all the limitation of the basic model. And finally, only a reference, we can not only represent or apply the SN field for the delta sigma, but we can't consider any generalized reference variable, for instance, in multi-axial fatigue, as the Smith-Watson-Topper, Crossland-Fatimi-Sossi, anyway, because they are based in the compatibility condition, and this compatibility condition is applicable to any material and also to any reference variable. It means any driving force. So, according to the program, we are now discussing the phenomenological stochastic models of cumulative damage. So, the evolution of many cumulative damage phenomena, as for instance, fatigue, fracture, wear, keep, etc., usually exhibits sigmoidal shaped curves, which are related to different physical magnitudes, as I mentioned, and for instance, vacancy concentration, the acoustic emission, the deformation, anyway. And this, the developing fatigue fracture phenomena, phenomenological, hence many advantages for this, because we can establish the fundamentals of the phenomenon based on a statistical basis. We can profit of the experience already existing from the statistical theory in this kind of function. We can derive simple analytical expressions which permit the interpretation, physical interpretation of the parameters. And we can also recognize the twofold character in cumulative damage when we are only analyzing the terminal reference state of the variables. In this case, we are predicting when is the failure, but we can also be interested in analyzing the evolution of damage in the fatigue process on the fracture process. And also the advantage of using evaluation programs which are practically the same, because there is a unique base or a standard version, because the coincidence of the data assessment using similar analytical cumulative distribution functions and model parameters, so that this is very versatile, the focusing using the phenomenological models, and then can be very easy to be integrated in the general scheme of the structural integrity for this. So the proposed methodology consists in recognizing the lower bound and the upper bound of the record of the test. We have to consider adequately which are the scales in both main variable and reference variable defining the phenomena. It means the logarithmic or the linear scale can be given so different views of the phenomenon. And then once we recognize these both bounds there, then we can be using the normalization to transform the problem of this sample function in a cumulative distribution function, because according with the statistical theory, the cumulative distribution function can be defined as a function moving from 0 to 1, in which the evolution is always increasing, so monotonically increasing. Then automatically this can be defined as a cumulative distribution function. Then the question is, which family can be used for representing this cumulative distribution function? So in this case, we use the three examples of application to define the problem we are discussing. The first one is the problem statement, is the assessment of the fatigue results and definition of the SN film. And then, as mentioned, we use these models based on compatibility, which are regression Weibull models. And the aims or the objective of this model, which is based on compatibility, are the following. First, to define in a probabilistic way the SN field, which is only referred to the ultimate state, which is usually the failure. The second one is that this conforms a basis for the probabilistic cumulative damage calculation without probabilistic definition of the SN field. We cannot define the damage, cumulative damage, in a probabilistic manner. Then it is also interesting to get from the model the endurance limit, because as I mentioned before, we don't introduce in the derivation of the model the condition that the endurance limit exists. And this is a requirement given directly from the functional equation. And then it is also interested to extend the model to include the influence of the stress level. According to this, this will be handled by Sergio Blasón in his presentation in details and give so an idea about the advantages of implied in the model. In the second case, we are interested in analyzing the strain evolution in concrete under compressive fatigue loading from a dual perspective. One, only considering which is the prediction of the statistically distribution of the terminal state. And the other one is the definition of this stochastic sample function for the different specimens for this. And we are using the work of Poveda and al. In order to perform this study. The aims in this case are, first, definition of the damage evolution and to extend this to any stress level of the SN field. In this case, we are only, we dispose only on the results at a certain level, but with the normalizing property of our model for modeling the SN field can be extended to any stress level. In this case, we have some experimental results, and this is the fitting using this methodology, which can be considered practically perfect for this. Then for different specimens, we find a certain scatter in the curve. So we need also to establish the ultimate distribution of the failure. So, and we can finally define the cumulative distribution function of this expected lifetime according to the Weibull model. So the second one is the application of the cumulative damage prediction. So according to this, we analyze the scatter of this curve, and then we give a statistical proposal for using. Then we can also use this definition of the damage evolution in order to establish the criteria to define the limit state in the practical design for the compressive fatigue. And then we can also use as the model to interrupt the test prematurely and then to predict, although we can perform the test until the final failure, we can obtain a reliable damage evolution until failure. Then the Spark-Menzies equation is only a particular property of the model only in the middle region of the damage evolution curve. And then we can explain why the Spark-Menzies is correct in this region, and even generalizing this property for any part of the curve here, and without making previous results as required by the Sparks-Menzies equation. And then finally, this is the probabilistic analysis, as I mentioned, the distribution of the failure, and then according with the Weibull model. So these are the results as an example for different steel fiber reinforced concretes and for different degree of reinforcement. And we see the quality of the fitting and also the scatter, which must be statistically handled to predict a representative damage evolution for the next specimen we can test in this case. So the complete assessment as the dual encompasses the analytical definition of the damage evolution, the probabilistic analysis of the SN field, the probabilistic distribution of the single parameters. It means that if we are repeating with different specimens, we can observe how is the distribution, the variability of the parameter, the model parameter, with the advantage that these parameters are represented by physically. And then, so the restoration and prediction of the damage evolution in the running test, allowing this premature interruption here. And we can see here, this is the region where the Spark-Menzies equation is applied. And finally, this is the case of not fatigue, but this is a fracture phenomenon. The asymptotic fracture energy and the specific fracture energy is determined by a test, a P, force delta test, or CMOD record, which is censored at a certain point due to the test condition. The importance is not only as a fracture, because it provides information, for instance, related to energy, which can be used afterwards for the fatigue design. The aims of this phenomenological model is the analytical definition of the complete curve, not only from the one provided by the test, the interpretation of the model parameter, and defining the fundamental properties of the fatigue, the fracture behavior, then a more reliable calculation of the specific fracture energy, because we are fitting all the curve and not, as we will see, only the fitting from the last point of the curves in the interruption of the test. And then we consider that this constitutes the basis for new advances in the comprehension of the fracture process, and therefore also to be used in the fatigue prediction. In this case, we consider the sigmoidal shape of the energy in the advance of the test, and then with the normalization, we can consider that this sample function is a cumulative distribution function. In fact, we are not directly using the energy, but we are considering the PDF. It means the not the cumulative distribution function, but the frequency distribution. And then this frequency distribution, the completely has an area equal to 1. And then in this case, we can, using only 4 parameters, the 3 parameters of the distribution we are looking for, which happen to be a Fréchet distribution, and then the other one, which is scaling the area so that the complete area under the curve must be 1 as statistically required. And then we consider that the integral of the curve of the area under the curve extended to infinity. And then according to this, the generalized extreme value family is considered in order to see which is the reliable or the suitable family of curves to be used in this case. We perform the considerations using Weibull, Gumbel, and Fréchet, and the Fréchet proved to be the adequate one, which is possibly because the distribution of the curves is the tail of the distribution must be, in this case, conditioned by a distribution which has a minimum, but is a threshold for maxima, which is bounded in the lower part of the curve, and then is going to infinity. And after the optimization of the parameters, we can find that an alternative to the current procedure, which is based on assuming an exponential curve for completing the part of the interrupted test in the laboratory. And then instead of this, we are defining the complete curve, and therefore the extrapolation, we consider that it must be some more reliable as the current procedure use. And the other question is that usually we can consider that this must be an exponential evolution of the energy, but according with the equation obtained with the threshold distribution, we see that it must be a combination of a power law and then an increasing exponential tending to the unity. It means that the threshold distribution is composed as a product of one increasing exponential tending to 1 and another power law which is reducing from infinity to practically to zero for this. And this must be perhaps giving us some information about the process which can be also applied in afterwards in the evolution of the fatigue process in the material. And so as concluding remarks, this is only referred to the last. So the proposed model should not be understood as a simple fitting proposal, but rather is to understand as a sample function which can be, once normalized, to be identified with one of the strength value family, which represent in some way so the response, the microstructural response of the material in the fatigue and the fracture process. So the information collected in the test record sometimes represent only a small fraction of the complete damage phenomenon. But because we are identifying this with a cumulative distribution function, so the procedure can complete this curve, even if we are considering only a fraction of the complete procedure. And then sometimes, because the shape of the cumulative distribution function is determined by the shape parameter, then in the Weibull parameter is less than 2 or even less than 1. We have no sigmoidal shape of the cumulative damage sample, but this is only so some to justify phenomena which are not observed as sigmoidal shape phenomena. And then the statistical background is not completely understood because in the most case, the extreme value distributions are the ones observed to be the best for the fitting. And we only know that there is so some theory, for instance, the Bogdanov-Kozin or Volotin, which interpreted that these are statistical processes in which a large number of primary elements are intervening in the material behavior. And therefore, the response of this can be interpreted as a statistical problem. And this is all in this introduction to the phenomenological model in fatigue. I thank you for your kind attention.
Thank you very much, Alfonso. So maybe if someone has a short question before we move to the next session. No? Then in that case, we leave it to the discussion time. And then let's see. Our next speaker is Sergio Blasón. He's working as a postdoc researcher at BAM, which is the Federal Institute of Material Research and Testing in Berlin, Germany. He defended his PhD thesis in 2019 at the University of Oviedo. He has experience in testing and evaluating fatigue tests with a special interest in modeling material behavior and statistical analysis. Sergio, go ahead.
Thank you, Rena, for your introduction. Can you watch my screen?
Yes.
Perfect. So, well, first of all, sorry, because I changed a little bit the original title of the talk, because we were talking about evaluation using MATLAB, but it's not necessary to use that software in order to evaluate the data. And basically, this talk is a continuation of the previous one by Professor Fernandez Cantelli. The intention is basically apply the phenomenological models that he was introducing in the first talk. And of course, I should remark that this is a working cooperation not only with Professor Fernandez Cantelli, but also with Professor Enrique Castillo. Well, this is a summary of the talk. Firstly, I will introduce shortly the topic, and then I will give you some examples of how we use the SM model in order to evaluate some experimental data. Then I will go to the duality in cyclic creep curves. I don't know if we will have time to go into the fourth and fifth topic, the damage accumulation under variable loading, and also the modeling of P-delta fracture curves. But in any case, maybe I can give you some small slides, and then we can talk about during the discussion time. Well, according to the topic, basically, as Professor Fernandez Cantelli mentioned before, we defend the interpretation of fatigue damage under two different perspectives. The first one, when we don't have any information about the evaluation of the damage during the fatigue test, for example, we can, I'm looking for the pointer, sorry. Yeah, when we don't have any information about the evaluation of the damage could be referred to the crack size, the emission, acoustic emission, the strain, or whatever. Then we only are able to evaluate the terminal state. It could mean basically the failure, or maybe some particular limit state that we can define in advance. On the other hand, when we can monitoring the evolution of the crack size, of the strain, or whatever, we can do a complementary evaluation of the data, and this is more or less what we will see in this presentation. For example, one example of the terminal state evaluation is the typical SM field, when we have many data, but we can say that every single test refers with only one particular point. So this means that, for example, we analyze this particular data under some specific stress level, and then we basically record the number of cycles till failure. We can do the same with the rest of the experimental data. On the other hand, when we can, for example, monitor the strain level along the cyclic creep curve, we collect basically many different points along one particular test. So we will see in this presentation how the methodology that we propose to evaluate each of these approaches. So first of all, I will explain how to evaluate the SM field from a probabilistic point of view by using the model that was explained by Professor Fernandez Cantelli before. And in this case, the model is implemented in a software called ProFatigue. And I will give you some details about that in the next slides. But in order to show you how to use the software and how to implement the model with some experimental data, I would like to take advantage of the experimental data collected by Holmen more than 40 years ago. I think also Professor Ruiz mentioned this work yesterday in the first talk. And he collected a lot of different results by using plain concrete specimens. And in this case, I will be focused on the specimens which were tested under constant amplitude loading. He was analyzing two different kind of tests. The first one referred to the S-mean equal to constant value. So basically, we can accept that the load ratio in such a cases were practically zero, so constant. And on the other hand, he was also evaluating some specimens under the same mean load. But in this case, the loading ratio was not constant, so I will refer only to this first case. At the same time, he got very good information using other specimens and their variable load histories. And we have some proposal to evaluate also this kind of tests, but as I said before, maybe I don't have time to go into detail, but in any case, we can discuss about that if we have time later. Well, basically, these were the results that he got when using the plain concrete specimens under the same minimum load during the test. He was using a frequency constant of 5 Hertz. And here you can see the stress level, referred to the comprehensive strength of the material. And as you can see, there are many data, experimental data. In total, 75 tests were tested. He got basically 15 specimens per each single loading level. Here you can see the numbers referring to the loading level. And in the lowest loading, he got 3 specimens were not broken. That's why we refer to them as runouts. Well, according to the typical models implemented in many guidelines and standards, we can basically analyze the data using a simplistic, in our opinion, model that consists basically in a linearization of the relationship between the lifetime and the stress level. So, which means that if we consider the lifetime in a logarithmic scale, basically we can use a linear relationship between the number of cycles and the stress level. So according to this, we can basically get this analytical expression that we can transform in a straight line, just taking the logs. At the same time, we can say that, okay, we can more or less identify the mean value of the life according to each level, but from a design point of view, we think that it's not practical or useful, because usually we don't take care about the mean value, but we should refer to the minimal percentage of failure, because of course we cannot think about a component with having a percentage of failure about 50%. Of course, we should minimize the probability of failure. That's why we should always take care about the minimum lifetime that we can expect under some particular loading level. So that's why we are a bit skeptical about this kind of analysis where we are focused on the mean value. Apart from that, another important remark is the evolution of the scatter along the Essen field. Usually, in the standards also, they promote some kind of constant dispersion along the whole stress level, in the y-axis, let's say. But we know that from a practical point of view, this is not like this, because usually the scatter in the highest levels are much lower than the ones compared with the lower levels, as you can see in this representation. So that's why, for example, if we take into account the model proposed by Enrique Castillo and Alfonso Fernández Cantelli, they let us to evaluate the data considering different scatter along the SM2, which is, in our opinion, an important advance. So let me introduce the software now, and you can access to the files through this link. You can use for free. In principle, there shouldn't be any problem when you download the software. And the software was evaluated some years ago in a cooperation between the University of Oviedo, the University of Cantabria, and the EMPA in Zurich. Here again, the link, if you are interested in, and also there you can find the typical two versions under 32 bits and 64 bits, and also some literature explaining how it works and some examples of evaluation. Well, of course, I don't have time to explain every single option of the software. This is just a representation of the main windows. In my opinion, the software is very easy to use, so you can handle without any problem and any kind of, you don't need any knowledge before. Because basically what you need to introduce is this kind of files. So you only need a text file introducing this information. So basically 4 different columns. The first one refers to the number of cycles until failure, or maybe not until failure, but the number of cycles that you tested. It could be, I mean, every single test could be or not identified as a run out. So depending on your evaluation, you can introduce this information also. The second one is the stress level that you are using in your test. And then also something important is that we can even evaluate components or specimens with different sizes. So this is some kind of information you, for example, if you are collecting data from different sizes, as Professor Ruiz mentioned before, or today, or yesterday, sorry, you can give the information to the software, and then you can evaluate both samples with different sizes, which is, in my opinion, also a very good advantage compared with the typical models that you can find in the literature. So coming back to the analysis of the Holman data, here, this is basically the kind of percentile curves that we get when we evaluate this 75 test. So here I am representing the percentiles referring to the 0, 1, 5, 10, 50, and 99% of probability of failure. So of course, the mean value or the percentiles refers to the 50% of probability of failure is more or less in the mean, in the middle point in every single loading level. But of course, as I was remarking at the beginning, we should take care or pay attention particular to the lowest probability of failure. So that's why it's very important, or it's a good advantage to have this kind of model in order to characterize the lower probability of failure. Something that it's important to note also is that we can use the model in order to identify some kind of bias when we analyze the data. What I mean about that is because, for example, I am more expert in metals, but for example, here, if I am not wrong, we can probably identify some kind of plasticity effects in the highest level because we are very close to the compressive strength of the material. And even though we are working with concrete, in my opinion, could be some kind of minimal plasticity effects in the affected zone. So that's why maybe we can resort to the cumulative distribution function that we can collect using the model. Professor Fernandez-Cantelli was talking about the normalized variable V, which basically consists in a variable considering both the information from the lifetime and also from the stress levels, which means that we can basically summarize all the information collected in the SM field in a single cumulative distribution function. So all in all, what I want to say is that we can identify some bias in the evaluation of the data because, for example, here we can see that the highest values are all of them concentrated in the lowest probability of failure. So which means that, for example, in this case, we could evaluate again the data, but neglecting these values. And this is exactly what we are doing here in this slide. As you can see now, the general scatter is lower because basically we reject this data under the highest stress level. And this is why I am remarking here that I am neglecting the highest loading level. As you can see, again, we are basically showing the probability of failure referring to the 0, 1, 5, 10, 50, and 99% of probability of failure. And according to this, because sometimes maybe the stress level or the variable that we should consider maybe is not the most beneficial for our evaluation, maybe we can refer to another general variable some kind of energetic variable, basically something, for example, relating the stress level and also the strain. And this is what also Professor Fernando Catelli mentioned before. And this is something that we promote in this paper that we published recently. So if maybe you are interested in that, I could share with you this paper also. What I am trying to show here is that thanks to this model, we don't need to collect so many data in order to get a very accurate or some kind of precision in terms of the SN field. Here, what I did is basically take into account in a random way only one particular specimen per each level. So these are the ones represented here with the black circles. And as you can see, for example, in the case of the lowest level, by chance, it was the chosen was done with the lowest lifetime. So of course, this makes some kind of consequence when we evaluate the data, because then the mean value is basically passing by this particular point. But for example, if we repeat the analysis, instead of just taking one test per loading, but in this case, taking I can say 3 specimens per each level of load, we can see that now the SN field is much more realistic. But here I will remark that we are using just 15 tests instead of the original 75 tests. But apart from that, I would like also to remark that this is something that I was writing here, that we only need 3 experimental points in order to evaluate, or in order to have a first evaluation of the SN field. So, which means that from these first 3 specimens, maybe we can also use the software in order to update the next step, and according to this, try to identify different stress levels during the experimental campaign, which means that it's not only a tool in order to evaluate experimental data, but also we can use the model in order to update our experimental program along the experimental program. Sorry for repeating the same. Yeah, so now what I want to say, or what I am trying to show here, is a comparison between all the 4 cases that I was presenting before. So for doing that, I am basically paying attention to the 1% of probability of failure. And basically, we can see that all of them are more or less in agreement, especially when we compare, for example, the green line and the orange line, which are referring to the evaluation, but without considering the highest load level. And we can see that basically the curves are almost the same, which means that reducing the number of cycles, we are able to more or less reproduce the same results, but also not only in the mean values, but also in the lower percentage of failure, which is very important in our opinion. Of course, when we implement also the highest level, since we have a very low lifetimes, there is some kind of displacement to the left, right? So, which is, I mean, totally reasonable. Again, if we only compare the curves referred to the 50% of probability of failure, you can see that almost the 4 cases that I was showing you are almost the same, especially under the highest loading condition. Of course, when we also take into account the lower loads, when we are only evaluating 3 data, one data per each loading condition, of course, we have some difference. But all in all, I think that all of the evaluation are practically the same, which, in my opinion, this is something, a potential characteristic of the model. And once again, we compare now the evaluation considering all the results apart from the highest level, and also the ones considering only 3 specimens per each loading level, we can see that all the percentage curves are almost the same, which means that at the end, instead of using 60 specimens, we can obtain basically the same results, but only resorting to 12 specimens, which basically that means that we can reduce the time, of course, the cost, and we are basically obtaining the same accuracy in terms of the probability analysis, which is a very good news for us. Then I would like to go to the evaluation of the cyclic fit curves. And according to this, I will take advantage also of the results from our colleagues of Castilla-La Mancha. And basically here I am using the results that are referred in the paper of Poveda et al. Here we are evaluating concrete under compressive loads with different quantities of steel fiber. Here you can see the case of the plain concrete and also different quantities between 50 and 60 kilogram per meter cubic. What we are collecting in this kind of, or what our colleagues were collecting in this test were the strain according to the number of cycles along each test. So basically, going again to the dual approach that we are defending is that we can basically analyze the data taking into account just the terminal state. So basically, we can get some kind of distribution function according to the failure points, but at the same time, we can use the information recording around the test in order to characterize this kind of behavior, this kind of damage accumulation, try to characterize this general behavior, promote some analytical expression to characterize the behavior, and from that point, be able to do some kind of estimation in advance. So this is basically what we promote in our last paper, also published this year. And here, as was mentioned before by Professor Cantelli, we are able to reproduce the whole curve that we collect during the test. And at the same time, at some particular point, we are even able to interrupt the test and get a very good approximation of the number of cycles until failure, as is shown here. But let me first of all show you more or less some of the results. And here we are representing all the data collected by our colleagues in Castilla-La Mancha. And then the model, the phenomenological model that we propose is this one, which is based in a Weibull distribution for minima. So we have 4 different parameters, which allows us to represent every single curve. The 3 parameters refer to the Weibull distributions, which means the location, the scale parameter, and the shape parameter. And then an additional one referred to the number of cycles till failure. And one can think about, okay, the failure, we know this information, but not really, because usually we interrupt the test when we arrive to some particular strength level or maybe some terminal condition, but usually we don't have 2 different pieces. I mean, the specimen usually is not totally broken. So that's why we implement also one number of cycles, which represent basically the asymptotic value of in terms of number of cycles at the end of these curves. And as you can see in these 3 examples, we are able to reproduce in a very good way all the monitoring data. And under my point of view, the fitting curves can be considered almost perfect. But not only that, because at the same time, we can also interpret every single parameter from a physical point of view. What I want to say with this is that, for example, if we pay attention to the location parameter here, I am representing the cumulative distribution function referring to the parameters that were collecting, fitting the different quantities of fiber. And here we can see some kind of evolution depending on the quantity of fiber. Because, for example, the ones corresponding to the plain concrete, which is the black one, is here in the left part of the graph, but then there is some kind of evolution depending on the content of the fiber. So we can somehow relate the values of the parameters with the quantity of fiber. So all in all, basically, we could collect this information in order to anticipate or estimate which could be the optimal quantity of fiber in order to get the best solution or the best combination between the matrix of the concrete and the fiber content in order to get the best fatigue performance of the material. And once again, we can use this methodology in order to anticipate the number of cycles until failure, because we prove that even when we are only considering for example, the 50% of the initial curve, we are able to estimate the number of cycles until failure in a very good way, which means that maybe we can save time and we can more or less take advantage of the monitoring recording during the test. And because we know that during the test, the slope of the strain versus the number of cycles, which is basically the strain rate, is decreasing at the beginning until the inflection point where the slope start to increase again. So maybe we can combine the information and on the task with this approach in order to, for example, characterize the inflection point and, for example, interrupt the test in that moment, and then maybe we can use the same specimen to do some kind of variable loading analysis. Then, okay, here this is more or less a summary of both approaches, the one considering the evolution of the damage along the states, along each test. Then we can basically from this point do three different analyses. The first one is even establish some limit state of the strain level, which was also commented by Professor Witt yesterday. And then also we can analyze the behavior of the parameters and try to correlate it with the quantity of fiber. And as I mentioned just before, is do some kind of estimation of the number of cycles, but before the proper failure of the specimen. And at the same time, if we collect this information and we have also some kind of information coming from different stress levels, we can take advantage of the ProFatigue software in order to evaluate this data. And we can combine both approaches in order to have a very good representation of the general behavior of the concrete. And now I will go fastly around this topic referred to the damage accumulation under variable loading. And here it's because I don't know if you are familiar with this kind of rules referred to the damage accumulation. Probably the most known is the minor rule, but there are also non-linear rules like the one from Marco and Sterker, and so many others which were published in the last 70 years. But all in all, when we use one of them, it doesn't matter which one. For example, if we get some result referred to damage equal to 0.6, what does it mean? Could us predict how far the break point is? In our opinion, that is not possible. That is why we promote to use this kind of rules from a probabilistic point of view. We can make use of the ProFatigue software, some kind of analysis concerning the V variable in order to correlate the minor number, for example, with the probability of failure. This is something that you can, if you are interested, read in our paper 6 years ago, it was published. Basically, we know that, for example, the minor number equal to 1 is related with the 50% of probability of failure. But what about the 10% of probability of failure? But of course, we can do this kind of analysis in order to reproduce in a better way this kind of damage accumulation. And now, just to show you one more slide about how to use the models that we are proposed, but in this case refer to the fracture or the energy of fracture. In this case, we are showing this kind of test, the 3-point bending test. And this is something that was published also with my colleagues Cantelli, Castañón, Cifuentes, and Muñoz Calvente, and also Enrique Castillo. And these ones are the fitting curves performed by Laura Castañón-Jano from the University of Cantabria. And you can see that they are able to reproduce in a very good way the monitoring curves by using the probability density function of Frechet in this case. So I don't want to go in detail of this because I don't have time for more, but just to let you know about that. This was my presentation. So if you have any question, please let me know.
Thank you very much, Sergio. Any short comments from the audience? Otherwise, we move to the next. Yes, please, Gonzalo.
Well, thank you, Sergio, for your presentation. It is very, very good and enlightening as usual.
Thanks.
I would like to know. I mean, because when you were analyzing the SN curves, you are saying, okay, I'm thinking that the ones in which we are reaching the highest maximum stresses, we are going to assume that they have some plasticity and so on, so we are not relying on them. So what if the ones you don't rely are the ones in another level? Because, for instance, you have some phenomenon like this maturity induced by fatigue or whatever. So what I mean is that is it fair? Is it fair to despise some set of data just because you have an intuition that they are not valid?
Yeah, it's a good question, and probably my answer is it depends on your knowledge about the material, and if, my opinion, if you are able to anticipate some kind of bias in the condition during the test, I think you should take advantage of that and remove the evaluation. But in any case, even if we consider, for example, this data, the highest levels, in any case, we are obtaining a SN a probabilistic SN which is, let's say, more conservative, but which is, for us, is not a problem in principle. What I mean, because, for example, when we compare with the other one, neglecting the highest level, of course, the scatter is lower, but also the percentile corresponding to the 0% of probability of failure is going to the right. So which means that if we consider the original one as the reference one, we are under the safe condition, let's say. So for me, it wouldn't be a problem. I don't know if I am answering to your question.
No, yeah. I mean, of course, yeah. The only thing is that I mean, we also, in these type of models, which are phenomenological, we also should consider that there may be some type of changes within the specimen, within the microstructure or whatever, of which maybe we are not aware, or we are not completely aware. So, but I don't know, because as they are phenomenological, they are there because they respond to something. So later on, if we apply, I don't know, of course, I mean, statistical models are right, but at some point, maybe there is some divergence from what it is happening in reality. I don't know.
Yeah,
how can this be implemented? But
I have two comments about that. The first one is also that I don't know if it's really, you know, much more than me about concrete for sure. So I don't know if it's really realistic to consider this such a high level when we are evaluating concrete, because in principle, shouldn't be the case that some kind of structure is under so high condition. I don't know, but I have no idea. And the other comment is like, of course, as you said, maybe we are neglecting some important information which maybe could help us to introduce some kind of modification in the model in order to evaluate the data, considering all the data, but in a different way. So this is something that we need to also discover by implementing some different, I don't know, information. For example, if we are not only evaluating the stress level, but also you implement also some kind of factor related with the strain during the test, maybe we can discover some general parameter that we can use in order to evaluate the same data, but using not the stress level, but some energetic parameters. So maybe that could be the case, and we can use exactly the same model, because, for example, in this case, in the particular case of the SN field, it's not only that this is a phenomenological model, but it's also based on the statistical compatibility. So it's even stronger than the other approaches that we are presenting in this talk. So yeah, we could try to discover some kind of new variable in order to also don't reject the highest levels in this case.
Well, thank you very much. Thanks,
You're
Sergio.
May I add some points there? In my opinion, the problem is that the stress, the maximum stress, is not the adequate parameter to be considered in the SN field, because we are assuming that the model is, or the results are, how can I say, the elasticity theory, I mean, in the elastic domain, is extrapolated practically without limitation. And in fact, it's not so, because the sigma epsilon diagram is not linear indefinitely up to infinity, but at a certain point. So the SN field would be valid, that the results we are getting in the test, only if the sigma maximum is the less than the limit, the elastic limit of the material. If we are trespassing this point there, then we have find another parameter, so that S max is not the adequate one. And then in this case, we can apply the model. So this is the question. And I suppose that at least the two levels, the two higher levels in this case, we are up the elastic limit of the material, and therefore are not valid to be considered in the evaluation. So we can discuss this in other occasion, but I think the problem is that we are considering delta sigma in the normal case of metals, or sigma max in the case of concrete, as a valid parameter to be used in the SN field assessment. And this is not true. And therefore, the people are assuming that this is a sigmoidal shape, but then other problems appear with the compatibility condition, so that we don't trust on a SN field which has this sigmoidal shape.
No, but well, I agree with what you are saying. So maybe putting some conditions also for the testing, but in any case, this also implies that you are assuming that the material has a certain behavior. So for instance, if you assume that concrete is linear elastic, I mean this, you know that this material does not exist, because the concrete is not like that. So what I mean is that, of course, you have non-linearities, and not only that, I mean, for instance, I don't think that well, it can behave in a plastic way in some cases, but only when you have a lot of confinement, and it is not real plasticity, so it is a different thing. So you also have creep. You also may have an evolution of the microstructure. So what I mean is that, of course, if when modeling this particular material, either you go to a full phenomenological model, which is data driven. I mean, as people like to say today, like data driven mechanics. So we are only going to be based on the data that we are receiving, and then we get rid of any pre-assumption for the material. Or we try to accommodate, let's say, the real constitutive behavior of the material, which, when, of course, if you trespass a certain threshold, it starts behaving in a non-linear fashion. Well, I don't know, but it is, I mean, it is just that these limits in the approach, I mean, they are also important, because models have to be tested also by the asymptotic behavior, as you were also highlighting in some of parts of your presentation. But in any case, I mean, of course, it is a very interesting topic, and I mean, the work that both of you did is really amazing. I mean, my congratulations.
Thank you.
Thanks.
Maybe I see Jose Joaquin has another question, but if you don't mind, we leave it for the discussion time.
Okay, perfect.
Okay, so that we are 20 minutes late, then let's ask for our next speaker with Carlos Rios. Carlos, are you there?
Yes, hi Rena. Hi everybody, I'm here.
Good morning. So
Good morning.
Let me see. Carlos Rios is our civil engineer with more than 20 years of experience in structure projects of bridges, supporting structures for onshore and offshore wind turbines. So he's the head of structures for renewable energy in their company, EDEM, which is a tiling company. Also, he's a member of several working groups on fatigue, structural concrete, and fiber reinforced concrete. So I think he's the perfect candidate for us to talk about Eurocode 2. Go ahead, Carlos.
Okay, thank you very much, Rina. I'm going to share my screen. Okay, I'm going to start the presentation. Okay, sorry, because I was finishing. Okay, well, first of all, I would like to thank, of course, Angel and Rina and Gonzalo and everybody, okay, from the USLM, okay, for inviting me to this very interesting symposium. And also, I would like to say that, well, I think my presentation is going to be a little bit, different, okay, from the impressive presentations that we have heard this morning, okay? Because from a practitioner point of view, okay, from a practitioner engineer point of view, okay, I'm highly involved in the design of heavily fatigue loaded structures. Okay, what I would like to present is the novelties, okay, the what has changed in the new Eurocode, okay, which is now being almost finished. Okay, it is almost finished. Okay, right now it is a draft. Okay, it is not finished, but it is almost finished. Okay, and I am a member of the TDA 8, okay, which deals with fatigue, okay, fatigue of concrete, okay, of course, and reinforcement. And I've been highly involved, okay, in the writing of the corresponding chapters of the new Eurocode regarding fatigue of concrete, okay. And also, I would like to say that I fear that maybe everybody's going to think that, of course, all the research of this great research about fatigue of concrete, okay, is not put there in the codes, in the standards, in the new standard, okay. Well, it is. I think it is true, okay. The Eurocode, okay, it's a standard that the engineer should comply with, okay, that's for sure. But it gives the minimum tools, okay, for fatigue design of concrete, okay. You need, okay, to go beyond, okay. You have to, well, consult other sources, okay, go to researchers, etc., etc. Okay, so this is like a warning, okay, because as you will see, there are no significant changes, okay, in the new Eurocode regarding fatigue of concrete, and a lot of research is not there, okay. Well, let's start, okay. So, as I said, I am commenting, okay, I am presenting the novelties regarding fatigue assessment of concrete structures in the new Eurocode, which is still a draft, okay? But significant changes are not expected, okay? Well, main change, okay, in the new Eurocode is the new SN curves, okay, the SN fields, okay. Just a small introduction, okay. Until 5 years ago or so, okay, the standard code, okay, or recommendation for verification of the ultimate limited state of fatigue of concrete under compression cycles was the model code 90, okay. The model code 90 was the first code which has a complete formulation for the assessment of the concrete under compressive cycles, okay. These, I'm sorry, because there are some noise, sorry. I'm closing the window, okay. So the formulation in the model code 90, okay, well, it was a novelty and it was a big step from my point of view, okay, but it was known that it was too conservative, okay, it was too conservative. So in the model code 2010, okay, new formulation, okay, from the University of Hanover, okay, from Professor Ludwig Lauhaus, okay, arise, okay, that formulation is in the model code 2010, okay, and well, this formulation improved the formal formulation of the model code, okay, with a well, significant improvement of the SN curves, okay. This new formulation from the model code 2010, okay, was based on high frequency testing, okay, which was an issue, okay, for a lot of people, okay. The testing backing up the formulation was made for both fiber reinforced concrete and plain concrete, okay. And as I said, it proposed new SN curves, okay, that improves the behavior of concrete under cyclic loads, okay. Main changes, okay, or main changes is the shape of the SN curve, and of course the parameter, okay, the reference parameter, which is famous between the practitioners engineers that are involved in fatigue design, which is FCD FAT, okay, which a lot of people understand it as a strength of concrete under one cycle, which is, of course, as you know, a wrong understanding of the parameter. Okay, but the model code 2010 changes. Okay, changed the definition of FCD FAT. Okay, but simply changing this parameter here from 250 in the model code 90 to 400 in model code 2010, and it was an improvement. Okay, this new formulation in model code, okay, for fatigue of concrete under compressive cyclic loads, okay, was followed up by the wind energy sector. Okay, mostly from people involved in the design of support structures, concrete support structures for wind turbines, because as you perfectly know, support structures for wind turbines are very highly fatigue loaded. Okay, fatigue is a very important topic in the design of this kind of structures. Okay, so people from the sector wanted a new formulation because everybody knew that formulation, the model code 90, was very conservative. Okay, and well, as an example, okay, you can see here from a real tower, a certified tower, concrete tower, okay, from a very large wind turbine and a very high tower, okay, up to 165 meters, okay. You can see here the damage along the height of the tower calculated with the model code 90 and the model code 2010, okay. The red line, the vertical line, is the damage equal to 1, okay, and you can see that for model code 90, okay, a lot of sections, cross sections of the tower do not comply, okay, with the condition that the damage shall be less than 1, Okay, but with the new model code, every cross-sectional tower fulfills the verification. Okay, so this is an improvement because it implies a saving of materials, a reduction of thickness of concrete, etc., etc. Okay. What we have now in the current Euro code, okay, that is not supersede because as I said, the new Euro code is not ready. Okay, it is a draft. Okay, the current Euro code has a different shape of the SN curves. Okay, a little bit different shape of the SN curves, and the parameter. Okay, the reference parameter FCD FAT is the same that in model code 90. Okay, we can see that the formulation is the same. Okay, what does it mean? It means that with the current Eurocode, sometimes, okay, fatigue is the syndrome for highly stressed structures. Okay, but sometimes this fatigue, according to Eurocode 2, the current Eurocode 2, was not calculated or was not properly calculated. Okay, and it was it's design driven. Okay, because this parameter FCD FAT, which is a parameter defining the SN curves, can't be you can't have the stresses under any cyclic load larger than this parameter, okay, above this parameter, okay. And as you see, okay, here in this table, okay, this parameter, okay, is FCD FAT is very low, okay, and it is comparable, okay, to the limit, okay, for to avoid nonlinear creep in concrete, okay, which this limit, the limit to avoid nonlinear creep in concrete was a stress limit, okay, that a lot of times it was a determinant, okay, for the shape of the cross section of a bridge or anything, okay. So with the current formulation of the Eurocode 2, okay, fatigue is an issue, okay, and it is known that that's not true, okay, and that's not true, okay, because there are no fatigue-related pathologies in bridge, okay, according to my knowledge, okay, and well, I have in the working in the task group 8, okay, of the Eurocode, we discuss, okay, if there were pathologies, okay, related with fatigue in bridges, and nobody knew anything about that, okay, and well, there are some known pathologies, okay, in foundations, okay, for wind turbines, okay, but these pathologies that were mainly in all foundations with all designs, okay, for steel tower resting on a concrete foundation, okay, these pathologies, and well, we have made some forensic engineering in this kind of foundation. The cause of these pathologies were fatigue related, okay, but not because the formulation or the ESN curves were unconservative, but because there were no proper assessment of fatigue, or, for instance, confinement, static confinement was considered, okay, for the assessment of fatigue, etc., etc. Okay, and that is wrong. Okay, and then fatigue problems arose under the flanges, okay, of the steel towers inside the concrete, etc., etc. Okay, but it is known that the current formulation of the Eurocode 2, which is almost the same that the model code 90, was highly conservative. Okay, so a change was required. Okay, the current Eurocode is excessively conservative. Okay, so just speeding up a little bit. Okay, the main modification in the new Eurocode is to change the SN curves, okay, of concrete under compressive loading. Okay. And the method, okay, or the approach has been that the SN curves are the same, okay, same SN curves, the shape, okay, but the parameter, the reference parameter FCD fat has been changed, okay, and it is not the same than in the model code 2010. It is not the same, okay. Somebody out of the working group, the people who was working on fatigue, changed it, okay. And it's almost the same that with some additional coefficients, okay. But the formulation is very similar to the formulation for the design strength of concrete, the general formulation for design strength of concrete, okay. This change, okay, hadn't experimental support, okay, and there were some opposition for the members of TG8, okay, including myself, okay, but because somebody, okay, from upstairs, okay, changed it, okay, but without any experimental support, okay, because you can agree with the SN curves from the model code 2010, but there were experimental support, okay, but in this case there were not, okay. So there were some opposition, okay. Of course, the new FCD FAT was better than the FCD FAT from model code 90 and even from model code 2010. It was an improvement, okay. The new FCD FAT was clearly higher, okay, and always above the limit for non-linear creep, okay, in concrete, okay. So fatigue is not that design driven, okay, when you are designing a bridge or other kind of structure under cyclic loads, okay. But this problem that there was no experimental background for this, okay, was solved just making comparisons, okay, making comparisons, okay. We were under a lot of pressure, okay, and we made a lot of comparisons, okay, for a lot of cases, etc., okay. And of course, the improvement of the SN curves, okay, from the current Eurocode and the draft, okay, was high, a significant improvement compared with current Eurocode 2, okay. You can see here the SN curves, and you can see that, of course, the SN curves, okay, of the draft of the new Eurocode are much better than the current SN curves, okay. So the improvement is very high, okay. But when we compare, okay, with the SN curves of the model code 2010, okay, there are some improvement, okay, for high minimum compressive stress of the cycle, okay, but for a smaller minimum compressive stress of the cycle, the improvement is not small, and not always there is an improvement, okay. You can compare here, okay, the yellow line, the dotted line, and the continuous line, okay, and they are almost matching along the whole number of resisting cycles. The same for the red, the same for the blue, okay. Of course, in the green line, in the green SN curves from the draft, there is an improvement, okay, compared with the SN curves from the model code 2010, okay, but this is for a very, well, let's say, non-usual case, which is when we have a very high, very high minimum compressive stress in the cycle, okay. So it was accepted, okay, the new formulation, it was accepted. As I said, there was a lot of pressure, okay, and well, there were more comparisons, there were more verifications, etc., and differences between the proposed formulation for the draft and the formulation in the model code was well, almost non-significant, okay, or negligible, okay. So this was, okay, the main modification regarding fatigue of concrete, okay, both plain concrete and fiber reinforced concrete, because as I will comment later, okay, there are no difference between plain concrete and fiber reinforced concrete, okay, in the formulation of the draft of the new Eurocode, okay. So, as I said, this is the most important novelty. Okay, there are others, but they are related with mainly reinforcement and other things not strictly related to fatigue of concrete. Okay, under compression or under any other kind of stress state. Now, I would like to comment very quick. Okay, I would like to comment very quick if there are shortages. Okay, because there are shortages. Okay, in the new Eurocode. Okay, and all the working group was aware of it. Okay, but we don't have the time nor the possibility of implement, okay, some novelties in the new Eurocode compared with the former one, okay, because there were some opposition, understandable, okay, because some people thought that there were no sufficient enough theoretical and experimental background, etc., okay. And there are, as I said, shortages that I'm going to comment. Okay, these shortages that were discussed during the redaction, the writing of the new Eurocode was first of all, there are no consideration of tension or compression or tension compression cycles. Okay, no consideration at all. Okay, the concrete, if there are tensile stresses, shall be considered cracked. Okay. And this is not a bad assumption, okay, because all concrete structures which are not pre-stressed, they are going to crack, that's for sure, okay? So they're not going, any problem with the tensile or compression tension cycles, okay? It's not, you know, it's not, well, it can be neglected, more or less, okay? But this is not true, okay, in non-pre-stressed structures, okay, in pre-stressed structures, okay, because in pre-stressed structures, okay, depending on the level of pre-stress, okay, you can have structures, for instance, bridges, railway bridges near to the coast, etc., and they would be almost compressed for every cyclic load, except for some. So there will be some tensile cycles, etc., okay, and it shall be they shall be taken into account. And the same thing happens when you are designing a superstructure for a wind turbine. Okay, you can have tensile cycles. Okay, you are not sure that the concrete is going to crack. Okay, so you should consider these tensile cycles or tensile compressive cycles. Okay, but the current formulation, okay, which it can be found in the new model code, in the model code 2010, is quite conservative, quite conservative, okay, because the let's say FCTD FAT, okay, the reference strength, okay, for tensile stresses, okay, cyclic tensile stresses, is very low. Okay, it matches the design tensile strength of concrete, which is very low. Okay, very low. Okay, so the formulation was not useful as it is, and some colleagues thought that it was too conservative. Okay, too conservative, and it wasn't worth, okay, to put it in the new Eurocode. Okay, so no reference to tensile stress cycles, etc., was made in the new Eurocode. Okay, of course, the designer, the engineer, needs to be aware. Okay, of if they are relying on tensile strength of concrete under cyclic loads. Okay, a Eurocode is not covering it. Okay. Other thing was frequency. Okay. As I mentioned before, testing for supporting the new model code SN course was a very high frequency testing, okay, and well, a lot of experts commented at that time that was not correct because fatigue strength of concrete highly depends on the frequency of the load, okay? And that's true, okay? That's true, and there is a lot of research, okay? A lot of that research coming from the UCLM, etc., that it shows, okay, proves that frequency is important, okay, when we are trying to define the fatigue strength of concrete, okay? Nevertheless, it is clear, okay, that common limits between 0.1 and 0.3 hertz, okay, limits which are considered the frequency limit where fatigue strength of concrete could be reduced significantly, okay. They are not common in standard civil structures under fatigue like railway bridges, of course. But according to my experience, they are not common, okay, for superstructures for wind turbines, okay. That was the main fear, okay, when dealing with the frequency of the load, okay. Here you can see an example of a real time series of a wind turbine on a concrete tower. Okay, you can see here, okay, some normal, okay, compressive stresses on the concrete tower. Okay, you can see here the stress time history. Okay, and if we zoom, okay, here where are the most damaging stresses, okay, of the time series, okay, and you take a closer look, okay, you can see more or less in an approximate way, okay, that the frequency, okay, of the stress, okay, is around 0.6 hertz, okay, and 0.6 hertz, okay, is clearly above, okay, those the limits between 0.1 and 0.3 hertz, okay, and this time series was the most damaging series of this specific concrete tower and wind turbine, okay, and we can see here, okay, that we have frequencies above the common limit of the suggested limits, okay. So I think that you have to keep in mind that frequency is important, okay, and you need to keep in mind that you need to know what are the frequency of your loads if your structure is very highly fatigue sensitive, okay. But for standard, more or less standard, because this is not a standard, this kind of analysis is not a standard, but for common design, for superstructures, for wind turbines, and of course for high-speed railway bridges, etc., okay, frequency should not be a problem, okay. Another shortage that it was decided not to include, okay, was the humidity, okay, the content of water in concrete, okay. There are some contradiction, okay, because some people said that, of course, okay, but this Eurocode is not going to deal, for instance, with offshore structures, okay. Maybe it can deal with, so if the new Eurocode doesn't deal with offshore structures, no problem with concrete in water, okay? But this was stated in the current, this is stated in the current Eurocode 2, okay? A particular aspect of special type of civil engineering works, offshore platforms, for instance, okay? Or any concrete structure, okay, in close contact with water, okay? But in the new draft, the offshore structures or liquid retaining structures have been removed, okay? They are not mentioned, okay? So that it's maybe a problem. And of course, there are other codes and standards like the recommendations or the guideline from the certification body, the DNV, okay, ST0126, okay, which deals with concrete in water, okay, and of course it implements a reduction of the resisting cycles if the concrete is in water, and we have compressive cycles, and a larger reduction if the cycles are compression tension, okay. This standard is based on another standard, okay, from DNV, which is also based, okay, on the old Norwegian concrete code, okay, And this Norwegian concrete code, these recommendations for the assessment of fatigue of concrete, if the concrete was in water, came from testing in the 80s, okay, for fatigue of these concrete in water for concrete structures for oil and gas in the North Sea, okay. So testing was let's say all okay, etc., etc. There were no novelties regarding this kind of assessment of concrete in water, etc., etc. And it was decided, okay, to let it out, okay, not include this humidity, okay. Another thing is the multi-axial. I'm finishing. Is multi-axial stress states, okay. They are not explicitly considered, okay. And there is a clear extrapolation of static approaches, strat limits for FCD, etc., okay, and also for confinement, etc., okay. Now, for instance, when you are checking the compression strat, due to shear, okay, in concrete, you are going to apply the same reduction factor, okay, due to transfer tensile stresses, to transfer cracking, etc., that you use for static cases, okay, and that's all, okay. According to my knowledge, there are or no test or not experimental background or minimum experimental background regarding these multi-axial stress states when you are dealing with fatigue, okay. Of course, you can take advantage that in the new Eurocode there is a refinement in the analysis, in the assessment of the shear, okay. And now the reduction of strength due to diagonal or perpendicular tensile stresses to the main compressive stress, okay, these reduction factors are, refined, okay, they are more accurate, okay, but they are always static, okay. You can, trust on these coefficients, okay, for cyclic load. Of course, maybe they are too conservative, or maybe they are not, okay. But for now, this is the only tool that we have, okay. Another thing which is important is the confinement, okay, because you can take advantage of confinement in a lot of details of a lot of structures, okay, mainly for wind turbines, okay. But can you take advantage of the confinement of the concrete for fatigue? There are some testing, there are some experimental background. To my knowledge, there is not, okay. And people is using it, okay. A lot of problems in foundations for concrete foundations for wind turbine came from consideration of a static confinement, okay, which almost doubled, okay, the strength, the fatigue strength of concrete, okay. But there are no experimental background. There is a recommendation in the DMV, which limits the confinement, okay, if you are dealing with fatigue, to 30%, okay, of the fatigue strength, okay, of the FCD FAT, okay, let's say, okay, and also this came from this extensive testing campaign, okay, in the 80s for the offshore concrete structures built in the North Sea in Norway, okay, and this. Could be this was not included in the draft, okay, because people thought that we are relying on just one recommendation, okay, from just one code, okay, and that's that, okay. But now you can't use confinement according to the Eurocode, okay. You need to reference this recommendation, because in the new draft of the Eurocode there are no reference to confinement. A confinement is an improvement, so you can use static results, okay, the static values for the confinement of concrete, okay. And of course, there are also a lot of problems that in my company, okay, in my department, okay, we are dealing all the time, okay, which are the stress concentrations, okay, stress concentrations that that in steel they are the day-to-day, okay, you have to deal with the stress concentration. But in concrete, stress concentrations are not known. You don't deal with the stress concentration, okay? Of course, absolutely not under ultimate limited state design, okay? Because you always, there is plastification of concrete, there is cracking, and also for serviceability limited state. But in fatigue, you don't have. You need to carefully consider the possible stress concentrations, okay? there are some recommendations, okay, and one recommendation was included in the new draft, okay, for some redistribution of stresses if you have a linear gradient of the stresses. Okay, in the Model Code 2010 and Model Code 90, there was a refined method to consider, okay, a possible redistribution of the stresses under fatigue load, or you have a stress gradient, okay. In the new Eurocode, it has been included, okay, but in a very simplified way, okay, because you need to check fatigue of concrete not at the most outer fiber, okay, the most loaded fiber, but 100 okay, from that fiber, okay, which is a way to redistribute stresses. But in our day-to-day work, okay, we found a lot of problems regarding stress concentrations. Okay, we have problems dealing with the mesh size of the finite element model, how to redistribute this stress concentration. It is a problem that it is not solved. Okay, of course, in the new Eurocode there is a step forward. Okay, which is to include this very simplified redistribution. Okay, but of course, if you need to be more accurate, you have to deal with it in another way. And last, okay, there is no direct reference to FRC, the fiber reinforced concrete. There are no reference, there are no recommendations. They don't provide a different SN course, okay, etc., etc. I know that this is a very complex field, okay, very complex field, but I think it's already known that usually, okay, fiber reinforced concrete has a better behavior under fatigue loads than plain concrete, okay. But as I said, the SN curve is the same for the plain concrete and FRC, okay? And of course, for multi-axial stress states, okay, FRC shall improve the behavior of concrete, okay? But sometimes you find another problems, okay? Now we are dealing with a fiber reinforced concrete tower for a wind turbine, okay? And we are thinking, okay, we are having fiber reinforced concrete. We have SN curves, okay, from test, okay, that's everything's okay. But we have also zones where there is a high confinement, okay. We can mix, okay, the improved SN curves of the fiber reinforced concrete with the confinement. There is no answer. There is no testing, okay. There is no experimental background, etc., okay. So it was decided, okay, to not include any reference to fatigue of fiber reinforced concrete, okay, because a lot of people thought that, well, it is not absolutely clear, okay, what are the approaches, what are the SN curves, etc., okay. And well, that's all. Thank you for your attention, and that's all. Thank you.
Thank you, Carlos. I was going to remind you that our time is up. Seems really from the Eurocode, there's a lot of distance from the research and the practice, right? Now our session is open for discussion. We can, let's see, the discussion is open for all three talks. And I remember that Jose Joaquin had one question. Are you there, Jose Joaquin?
Hi, yes. Well, my question was for the previous presentation. But in any case, thank you for the three speakers for their presentations. My question was for Sergio Blasón, or even for Professor Fernández Cantelli, because he's also an author of the method. I'm very interested in your model, and in fact, I have applied the model for the fatigue creep curve in our study about the size effect in fatigue of cubes. Well, when applying the method, I know how to fit this generalized value, extreme value distribution to a complete curve. but I need some clarification or explanation about how to use it for incomplete tests. For example, like a run out that you have to stop the test and you don't know how much fatigue life you have already consumed during the test.
So can you hear me?
Yes.
Yes.
So we are referring to this kind of, let me say maybe the screen. We are speaking of this kind of data, right? So
Yeah, exactly for that case.
okay. So I think in our experience, because you already know that we were playing with these results from Elisa and your colleagues, we were exploring the possibility of take advantage of the registering data and try to do some kind of extrapolation of the data in order to characterize or try to anticipate the number of cycles till the end. So I don't know if this is in this regard your question.
Yes.
So basically, because the origin, also the model is here, this analytical expression. Basically here we only need the number of cycles that you were recording, also the strength that you are measuring. And from that point, if you apply the fitting curve, let's say, you should be able to characterize the complete curve. From that point, you will obtain probably the 4 parameters. And for example, the one which is here in red color, the number of cycles, should be the hypothetical number of cycles till failure that you could use as your anticipated failure point. But I don't know if that was exactly your question. There is something more deeper.
For example, I have a group of complete tests. No, you can obtain those parameters for each one of those tests, and you can get like a master curve that represent them all. No? If you normalize the variables, all those different curves collapsed to only one. So that's very interesting. However, in an incomplete test, how do you know? I think for someone that, like me, that I don't know much about probabilistic distribution, how to fit them properly. But if you have only the first part, maybe you know that's you have reached a 20% of the fatigue life of that specimen. Okay, you can fit that experimental curve versus the first 20% of the distribution. But if you don't know where you are, how do you fit the distribution to your curve in order to extrapolate when this specimen will fail?
Yeah, I assume that you are also asking because I was paying attention yesterday to the talk, and basically you are performing this kind of distribution right here, but in using not the PDF but the cumulative distribution function. And basically nowadays you are collecting failures with runouts, right? At the same time, so it's difficult to characterize the cumulative distribution function. And I am totally agree with you. So I will say that maybe you can, I don't know what is the opinion from Alfonso, but maybe you can use this kind of methodology that I mentioned just before in order to try to transform the runouts in some hypothetical number of cycles until failure. And from that point, see if they are more or less in good agreement with the typical sigmoidal shape that we got when we usually fit this kind of results.
In fact,
that's
similar to what I try to do is like, well, let's consider different numbers. I perform like a sweep, sweeping from 10% to 90% of the fatigue life and comparing when the fit was the best one. but I don't know if that's the correct procedure.
Yeah. I think it's not easy because, of course, we are basically mixing different specimens, one which are totally broken and some ones which are not. So I assume that it's a difficult issue. But in fact, for example, in the SN program, the one which is we commented before, we also, let me take advantage of this slide, also because in the model is also implemented the information from the runouts. And in some way, this model also is able to try to estimate the number of cycles that we could expect in the runouts. So which means that we are doing exactly more or less the same kind of analysis here, even in the SN model. So I don't know if Alfonso has some kind of comment on that.
I don't know.
It's there, right?
And another problem, it's similar to what Gonzalo Ruiz has said before. When I have observed in many cases of runouts that the epsilon n curve changes its behavior because of this fatigue maturation that we are observing. So as the material is evolving, the material properties are changing. That's why all the curve also changes, and it doesn't follow this homogeneous shape of cumulative distribution. Okay, well, thank you.
May I make some comments about the question? First, if you are only interested in the prediction of the lifetime, then you are referred only to the estimation of the NF, the final number of cycles. So, and if you have some results, you have the distribution of this NF, so that practically you can predict which is the lifetime for the next specimen. The other question is, if you want, additionally, to know how is the evolution of the damage in a possible future test. And then the only possibility we think is to consider the dual approach. It means to represent the normalizing curves all together, and then to study the parameter, the variable parameter defining these curves there. So because normally the parameter will have a certain variability, and then theoretically, as we talk with Castillo, Professor Castillo, we need to perform a bias study of this parameter, and this is not yet solved because we need so much more specimen tests to perform this distribution of the 4 parameters we are using in this. But note that the parameter, the NF, the lifetime, this is a parameter of the model. And then only considering this, you can predict the lifetime of another test. But if you want to also to describe the evolution of the damage, then this is more complex because you are to consider the 4 parameters together and to see the variability and the correlation of all them.
Okay.
And then with the maturation, I agree, but so we are step by step, and so we hope to solve the first step. It means to confirm that the model is correct, and then perhaps you can introduce the modification of the condition of the material. But from the very beginning, this is not possible, I think.
Okay, thank you.
Thank you very much.
More comments from the audience for our straight talks? Yes, I think there's Jose Angel Rodrigo.
Hello. I first of all thank you again for all your 3 presentations today. They've been really good and really insightful. I have, I mean, as a professional, a principal engineer on United Kingdom, and we've done a lot of work with foundations for wind turbine foundations. So I have a query for Carlos Rios on the last presentation, which has been really good. Actually, I think it's not just been on Eurocode. I think it's put all of it together with the different codes that we use, model code 2010, 1990. So my question was with respect to Eurocode 2. I am aware.
Carlos, are you there?
Carlos, are you there?
I am. I'm hearing.
So in
Yes.
addition to the fatigue formulation on Eurocode 2 part 1.1, on the part Eurocode 2 part 2, which is used for bridges, there's also on section. I can share my screen if you want. Actually,
Okay.
I think that make it easier. On this in this bridges code, there's also a formulation here for calculation of fatigue damage on concrete using Parker-Minor rule.
Yes.
And obviously, as you mentioned here, the FCD FAT is changed. This is 250. So my question will be, will we be? Do you know? I mean, it might be that because this is a different code, nothing has changed. But will we be able to use this formulation, but with a new revised FCD FAT, or this is totally separate?
No, it's the same. Okay, but when I was saying that the shape of the SN curve, okay, but because that is an SN curve, okay, it was kept. Okay, is that there are no changes in the SN curve, okay, and you only have to change the definition of FCD FAT. Okay, so all the curves. You know, that formula is absolutely the same. Okay, so that won't change.
Okay, no, that's really good. I mean, I mean, I totally agree with all what you say. I mean, previously I used to work in Spain also with some precast concrete towers, and on all the foundations that we done here in the UK, we are aware of how conservative some of the approaches, such as you say on Eurocode 2 and a model code 1990 was. So I'm really happy to hear that the industry is moving forward on that direction.
Okay, glad to hear that. Okay, because I think that there is an improvement. Of course, as Rena said, distance from codes and research is, I think it's excessive. Okay, I do agree. Okay, but this what we have right now, we can change that. Okay, so this little step, okay, I think it would be better. Okay, for sustainability, reduction of material savings, etc.
I do have another question, but I think
yes.
I know the answer to that. But again, for you, Carlos, which is that I assume that this new research of concrete strengthening under fatigue that is not included on Eurocode 2 or any code.
What is the new
you know, on Gonzalo's presentation on day one, you know, when he mentions this phenomenon of concrete increasing the strength under fatigue.
That is not included, okay, and let me say that every college, okay, that were working with me in these working groups, etc., was, you know, they are very good professionals, and they are you know, very good wise engineers, okay, but that increase of strength, okay, because of fatigue, it's going to be hard, okay, to put it in the code. Okay, it's going to be hard.
Yeah, no, I expect so.
And I do not agree, okay, because it makes no sense that people are researching or testing, etc., and they are, you know, demonstrating, they are, you know, proving their results, etc., but you know, the standards, the codes, etc., are conservative, okay. They are conservative, okay, and they are a little bit afraid of any innovation. It has to be very, very clear, okay. So there won't be, I think, it will take some years, okay, to implement all these you know, research in the Eurocodes.
Of course, I mean that's what I would expect. As you mentioned, the code is sort of almost like a legal thing, and it had to be.
Yeah.
Yeah. No, thanks a lot for.
Okay, thank you, sir.
Gonzalo, please jump in. Maybe you want to comment since?
Well, no. Well, I also would like to wanted to thank Carlos for his presentation, and because it is also always very good to have the view of people who are more in the side of the technology. I mean, the real technology, the technology that is being used, and the codes and so on. And also Jose Rodrigo for his comments. I mean, it's been very good. I just wanted to ask you, Carlos, whether you at some point have discussed what is the way of testing concrete in order to know what are the fatigue properties, because yesterday I was showing something which for me is it is striking, which is that you change the shape of the specimen and then you are getting very different results. And then now for me, it is very clear that many of the curves that are in the codes, they have been obtained with specimens. I mean, even the shape of the specimen is not registered, so you don't know exactly what was the shape of the specimen or even the size. So did at any moment, I mean, was there any discussion on this topic in the TG8?
There wasn't, Gonzalo. There wasn't at all. Okay, and this is more this is new for me. But there was any discussion. Maybe you could expect it from House or somebody. Okay, but there were no discussion at all. Okay, you know that the curves, okay, that are in the code, okay, are based in just one parameter, which is the characteristic strength of concrete. Okay, and that's that. Okay, of course you can always make your test. Okay, this is allowed, okay, by the Eurocode, the design assisted by testing, as you know. Okay, but regarding any influence of the shape of the specimen, etc., there was absolutely no testing there. Everybody assumes that you test specimens for the characteristic to get the characteristic strength of concrete, and you have the SM curves for fatigue. Okay, and I know that's not true. That's a that's a very a gross simplification, but that's that. Okay.
Well, well, thank you. I imagine that, but I mean, I think that these experimental details are very important, and at some point, maybe I don't know, we should have make the proposal to do like a group in order to develop like a methodology for testing, because I mean, another important point is like the eccentricity of the loading,
Yeah.
because as you saw yesterday, you just change just the hinge, and then you are getting like one order of magnitude shift in the SN curve. Well, in the SN curve or in the probability curve, well, which is important. And just a comment, I mean, to what you were saying, well, two comments. One of them is that I believe that using fibers, I mean, well, fibers are not well treated in the new Aero code. You know that an Excel is not going to be mandatory. It is going to be only informative. Which this is something that I don't really understand. And even an Excel doesn't really deal about the improvements or the enhancement that you can get in the performance in fatigue with fibers. But well, this is, and the other comment is that well, I believe that fibers somehow work in this confinement that you were mentioning, because fibers are kind of confining the material. So whenever you have a confinement, it is true that you should have also an enhancement in the properties of concrete in resisting fatigue. And well, and then my last comment is that, well, you said that maybe in a few years, some of these new things that we are doing in research are going to be considered, but we are patient. So we are going to go on and let's see whether at some point people try to improve. Like, I mean, some of the things that you said, well, this no tension approach, which is, I don't know, I mean, it is incredible that we still have this, and we don't try to take advantage of properties in tension or of fatigue or fibers or these type of things. But there is a lot of research, as you saw, done on the behavior of fiber reinforced concrete in fatigue. So at some point they will have to read the papers.
Yeah, I totally agree with you, Gonzalo, because as you know, I'm aware of all your research, okay, and one thing is true, okay, when you know that in the industry, okay, you know that renewable energies, wind energy is going to be okay the next big thing. It is already okay, but in the next years, okay, offshore wind turbines, they are going to be built, okay, in thousands, okay, and there are going to be a lot of investment, etc., etc. And people designing concrete these kind of structures, they are testing, okay, they are not, you know, just looking at the code, okay, and applying the formulation, etc. They are testing, okay. So this is related with your first question, okay. Of course, that would be great, okay, because people shall know how to test, okay, must know how to test, okay, because that's very important, okay. And regarding, you know, all the implementation of all these research, it was a little bit disappointment, and I think I talked with you about this. It was a little bit disappointment, but on the other hand, I understand that there are reticences because of mainly of people that is not involved in fatigue or design or fatigue research, etc., etc. Okay, they think in another way. Okay, slowly, that's true, but I'm sure, okay, that before we finish this decade, okay, we will see some improvement in the codes. A lot of this research that you're doing, okay, in the codes. Okay.
Thank you, Carlos, and also thank you for being here.
Thank you, Gonzalo. Rena.
Any other comments from the audience? Otherwise, I would like to thank our speakers for those 2 days, and for all the audience. Thank you very much to you all, and I hope really there will be some. We have learned something through this 2-day workshop, and there's an exchange from the academics and from the practical engineers. Thank you very much to you all. Alfonso, do you want to say something? Alfonso, you are silenced.
The workshop was very instructing to me, because I learned a lot of the problems in concrete. And after the very good presentation of Carlos Rios, I think there is a lot of to do and the Spanish group could be, I think, propose so many improvements about the Eurocode with the concrete. And I think it is very promising for the next workshop, because I think we get a lot of ideas, and so with our contacts, and so I hope to repeat so next year the same workshop. Thank you for all your effort in organizing the workshop, and as mentioned, this was really very instructive to me.
Thank you, Alfonso. Jose Angel.
Yeah, just a quick one. No a question. I wanted to know: is it possible to get a PDF copy of the presentations and this seminar? A video is going to be uploaded.
Yes. Actually, exactly. I mean, I was going to mention again for our speakers, because I have received like 3 PDFs from the 3 talks. And then for those of you, for Carlos, for Sergio, Miguel Angel, and then Jose Luis are not here. So please send me the PDF files, and we will upload it to the repository of SAMTA. So Jose Angel, if you maybe send an email to Angel, so that later on we can, let's say, we can send email to let people know where are those presentations. And also we have recorded the 2-day session, and then we will upload it to YouTube, and then later we'll send the links if you want to come back for the talks again.
Yeah, that's perfect. I mean, there's also more people there, for example, in my company, where we work in this type of projects that they were interested on this topic. So I want to basically spread it with them. Yeah.
Thank you very much.
Okay. Yeah. Thank you for everything.
You're welcome. Okay, so I think maybe it's time to close up this workshop, and I really hope that maybe next year we can meet again, or we can meet before, and to exchange ideas, to learn from each other. Thank you all for all the speakers and all our audiences. Thank you.
Thank you for the
Okay,
organization. Thank you for everything. Bye.
Thank you.
Thank you.
Thank you, Rina. Thank you,
Thank you.
everybody.
Bye-bye.
Bye. Bye.
Bye.
Bye.
Thank you. Juan.
Thank you.